All right, now we're recording. So, let people get out their stuff. These slides are also posted on the Canvas. And I think there's even handout versions where it's 6 slides to a page, so you can take notes around them if you want them. All right, so Chemical World, Chapter 1. So we're going to talk about things that are really, really small. And actually, I found a cool thing we're going to look at. Like sand is annoying because it's so small, right? It sticks to everything. But sand is composed of even smaller matter called atoms, which is what the primary thing that we're looking at in this class. And they are unimaginably small. So a single grain of sand contains more atoms than there are grains of sand on the largest beach. It's like that one grain of sand has more atoms than the beach that it's on, which very, very hard to put that into perspective. So the idea that matter is composed of tiny particles is like one of the greatest discoveries of mankind, because it's kind of like a car, right? Like if your car breaks down, if you don't know that it's made up of other smaller parts that might break, then you'll never know how to fix it. And as soon as you start looking into those smaller parts, you can figure out what makes the car work, and then you can fix it, or you can design a better car because you understand the pieces that make it up. So we're looking at the pieces of matter that make up everything. And by understanding those things, we can, well, manipulate and control the world around us. Okay, so this is the scale of everything. You can find this on YouTube. There are like videos that go through it. Where's that grain? There's a grain of rice. All right, so there's that grain of sand on the right there. I forget that I can't oh wait, I have a laser pointer. So yeah, grain of sand there on the right. Haha. All right, so you got the grain of sand on the right. And that's already pretty small because you're looking at like dust mites here, amoeba, a grain of salt. But we can keep going smaller. There's a silt particle, a skin cell, red blood cell, and we're still not at atoms or molecules. If we keep going, there's Mimi virus, there's the largest virus, bacteriophages, which are very cool, wavelength of ultraviolet light, Hep B, HIV, viruses. Now we're starting to see some of the biggest molecules. So DNA is a massive molecule, so is the phospholipid bilayer, which makes up the membranes of cells. Keep zooming in. Now we're at other proteins, other large molecules. The smallest molecule we've got now is a glucose molecule. And so down here at the bottom, we're going to talk about scientific notation, but that's times 10 to the negative 8 meters, I believe. So we're at teeny, teeny, tiny scales here. And so there's a water molecule and a carbon atom. And if we try to zoom all the way back out, oh, missed the grain of sand. Nope, that was the silt particle. There's a grain of sand, and then an ant. Right, so the stuff that we're working with, basically I don't expect you to have any intuitive sense of how atoms or molecules are going to work, because they're so small that unless you've like studied chemistry or watched chemistry videos on YouTube, there's like almost no connections, right? So part of what I want to try to do is build some connections, help build up that intuition. Because you're not going to be able to just guess at how things work, for the most part. We'll try and build up. So coming back to this idea of like understanding like these fundamental building blocks, to understand how matter behaves, we must understand how the particles that compose matter behave, right? So understanding the parts of the car to understand how the car works, understanding the molecules to understand how those parts can even be made. This is one that'll probably be on the test. All matter is composed of atoms and molecules. Maybe and or molecules. Molecules are groups of atoms bound together by chemical bonds. So a lot of the stuff, the things are not actually bound together by chemical bonds. Like all the water molecules in my coffee, well, each water molecule is made up of an oxygen, or those, yeah, they're labeled. So oxygen and 2 hydrogen atoms. The water molecules are not chemically bonded to each other. That's intermolecular forces, which comes later. So in theory, we could look at a water molecule and say, well, maybe it's a linear water molecule, but a linear water molecule will have different properties than this one that's sort of bent. So just because water is bent is actually what gives it a lot of its properties. So there's a direct connection between the world of atoms and molecules and the world we experience every day, right? Makes sense, because everything's made of atoms and molecules. So we're interacting with them just on large scales, right? Large groups. And chemistry is the science that tries to understand how matter behaves by studying how atoms and molecules behave. So if we look at atoms and molecules, if we understand those, how can we extrapolate those properties to this large scale that we live and exist at? This is one that I think I'll have a question like this on exams. But everything you can hold or touch is made of chemicals. I think in the news, popular media, like chemicals get treated as just things like paint thinner or PCBs or PFAS is another big one now, nitrates. Like you hear about these bad chemicals, but everything is a chemical, whether it's good or bad. The vegetables, organic vegetables, are made up of chemicals. So in this class, when you hear chemical, it's just everything. If it's a toxin, that's a bad chemical.
Everything that's liquid, right? Or no?
Everything.
Like materials?
Yeah, so like this, plastic is a chemical, wood's a chemical. It's like the super, super broad. Yeah, everything, even the air. So yeah, popular conceptions of chemicals limit them to dangerous poisons or pollutants. But that's not the case, at least in scientific terms. A lot of the times it's the dose that makes something toxic, right? Like you can die of water poisoning by drinking too much water, or salt poisoning. Even though we need salt, too much of it is a bad thing. It's just the chemicals that are talked about in the news and stuff, they're toxic at very low concentrations. It doesn't take a lot to cause adverse effects. So like the water we drink, air we breathe, food we eat, medicines, all of those, our bodies, are chemicals. So chemists are interested in why things are the way they are. So why is this plastic clear, but this plastic is not? What about those molecules causes that? Or why does wood burn, but metal doesn't really burn? Those are sort of the questions that chemistry answers. And one of the key ways that we do this is through the scientific method. And the scientific method can involve something as simple as, I guess for a piece of plastic, somebody had to make it. But maybe when they're first making plastics, they're like, mix this batch of chemicals together and it comes out clear. It's like, okay, why did that one come out clear, but this one wasn't? Then you start to look into the structures, you do some more digging, and you use the scientific method. So it's not a super rigid procedure. It's more of a general outline of reasoning. So ancient Greek philosophies were based on reason. And when I say based on reason, it was like logical strings of statements. I can't think of the exact one now, but people used to believe, not that long ago, like 1800s, that garlic would turn off magnets. So if you rubbed garlic on a magnet, the magnet would stop working. And there was a whole line of like logical statements that like tied that together, but nobody, I guess, tried it. I think magnets were fairly rare at the time, if they thought they were so magical. But you can look that up. It was a real thing until some guy was like, no, I rubbed this garlic on a magnet and it's still a magnet. Had to be tested. He tested it. And it took a while actually for people to completely buy into this scientific method. So the basic steps happen in this flowchart. Right, we start with an observation. So, oh, actually, here, I had this set up. So this is another thing that I want to use. Lost my mouse. Oh. Let's see if this is the right one. Yeah, okay. I don't know if you guys have used Mentimeter before. It's pretty cool. Or if you've used iClickers before, it's a very similar thing, but it's free. I like free. Okay, so the way this works, I'm going to try and use this more throughout the semester as well. If you go to that website at the top, www.menti.com, is that big enough for everybody to read? On your phone or whatever. This is maybe one of the few classes where I'm like, get your phone out. So yeah, go to menti.com and you type in that code. I think it'll be on the top of each of these slides. So use the scientific method to solve a problem. Do I need to write? Is it big enough? It's good. Okay. So let's say sometimes I get really bad stomach aches. So that's my observation. So now we're going to use the scientific method to try and figure out what could be going on there. Yeah. Taco Bell. Yeah. But it's so cheap. I guess that's the problem, maybe. Okay, so on this website, on this app now, once you've typed in that code, you can enter in some hypotheses and they'll pop up here. So why am I getting stomach ache sometimes? I guess we don't have to use this, but if you do use this, please, I'll write them on the board. Okay, so we got Taco Bell. Any other hypotheses? Food poisoning from Taco Bell? Or maybe I've got a gluten intolerance. Too much sugar. Or the other one I was thinking of was lactose intolerance. All right. So, good golly. Hey, the dinner you had, something you drank, not eating, food poisoning, yeah, lactose intolerance. Fluent intolerance. Oh, gluten, gotcha. Yeah. Okay, so we got some hypotheses here. Now, the next step of the scientific method, can I switch back and forth between these? It's not going to let me. Okay. Next step is to come up with, so these are our hypotheses. All right, plural. So how can we test some of these?
You can test the lactose by drinking milk or eating cheese.
Yeah.
Gluten by eating something that contains gluten.
Right.
It's kind of sketchy to test the food poisoning.
Food poisoning is a little bit difficult to test.
Yeah.
Yeah, that would be a little bit difficult to test. Taco Bell, just go eat Taco Bell and see what happens. I mean, for some of these, yeah, it's rolling the dice. If you want to maybe play it on the safe side, it's like if you're usually drinking milk or eating bread, cut those things out, right? So let's just pick one of these. We'll do Taco Bell first. And so let's say you go through the scientific process here. Let me pull this up. Okay, so if we're going through the scientific process, we've now got our hypotheses, or hypothesis, right, Taco Bell. So if we test that by going and we go and eat Taco Bell, maybe that doesn't do it. Maybe I get Taco Bell specifically like a burrito that doesn't have cheese, right? Like I don't get a quesarito, might be a bad choice. We'd have some conflicting data maybe. So if that doesn't fix the problem, and then our answer is no, then we have to go back and pick a new hypothesis, right? And then we run a different test. It's like, okay, I'm gonna eat an entire loaf of bread. And let's say I do that, and then I'm in agonizing pain, and I go to the hospital because I basically poisoned myself. That would be a pretty good sign that you have gluten intolerance. I wouldn't recommend doing it that way. Cut it out first, or eat a little bit. But that's kind of the scientific process, and you can and probably have applied it to your everyday life, right? Like when I'm watering my plants, if I turn the water on at the spigot and I go to use the hose and nothing comes out, well, there's probably a kink in the hose somewhere, right? And so it's something that you maybe are using just intuitively, naturally. It's kind of like a, right? Remove all the other variables. But now we're applying this to, scientific theories, which can get a little bit more complicated because there's a lot more variables involved. But that's the general idea. So again, our observation, for something like stomach aches, we can make an observation with a naked eye, and then test it too without use of instruments. But for other observations, we need to use sensitive instruments, especially in chemistry, dealing with atoms and molecules that are so small. I think I might have put these out of order, but a scientific example of the scientific process is Antoine Lavoisier, one of the founding fathers of chemistry, and his wife, actually, who was a chemist in her own right, Marianne. They were both studying chemistry, and Antoine and Marie, they put things into sealed containers and burned them, which, don't do this at home. It could explode. But they were doing that, and they observed that when they put their sealed glass thing on a scale and weighed it, and then they burned the thing inside, the mass didn't change. So whatever was happening inside in that burning process, it wasn't destroying anything, it wasn't creating anything, mass did the same. So then these observations led to hypotheses, and a good hypothesis is falsifiable, right? So for each of these things that we did, it's like, well, Taco Bell, I can test that. If I go to Taco Bell, eat Taco Bell, and I'm fine, then Taco Bell is not the reason that I'm having stomach problems. There are other things that are not falsifiable. You can't test a negative. So you can't say that nobody in the world, or that there aren't any unicorns in the world, because you'd have to go to literally everywhere on the earth and look for them. You say, probably aren't any, that's fine, but you can't prove a negative. So for Lavoisier, his hypothesis was that the combustion process involved combining a substance with a component of air. And so that air was inside the container, and so everything was self-contained. So then you go out and you do experiments. Again, right, we came up with some experiments to test my stomach problems. And these are, need to be highly controlled. So when I mentioned, if you go to Taco Bell, and this is one of your hypotheses, but lactose intolerance is also a hypothesis, don't order a quesarito that's full of cheese. Now you don't know if it's the Taco Bell or if it's the lactose intolerance. So you need to control for those kind of things that might be conflicting. And you might end up with, how do you make sure that you didn't get food poisoning at Taco Bell? Maybe you have to go, you did. But yeah, so you gotta test for these things. And then it has to be designed to validate or invalidate the hypotheses. A lot of times when you're doing survey work, so the problem with surveys is that most of the time, the only thing it can tell you for sure is what those people in the survey thought or felt. And then you have to consider okay, how many, the people who took the survey, am I just learning things about people who take surveys? Or does it say something about the general population? I don't take very many surveys. So then if there are hypotheses, or if the experiment shows your hypotheses to be incorrect, it's fine. You learned something by that. I think we get hung up on the idea of always having to be successful, but a big part of research, and I can attest, my PhD took 7 years. There's a lot of failures that happen along the way. And with each one, you're learning something more, though, to get you towards that correct hypothesis. So then you revise your hypothesis, or sometimes you have to discard it entirely, and then you move on and test it again. It's a very iterative process. You go through it a lot of times. So if you have a number of similar observations, they may lead to development of a scientific law. So scientific law are brief statements that summarize what happens and predict future observations. Right? We have the law of gravity. Right? If you're near a large object such as the Earth, if I take something and I drop it, it's going to fall. And that scientific law is built on the observation that every time somebody's done that on Earth, the thing falls. We've never observed it to not be true. But these are, again, subject to experimental testing. They've just undergone incredibly thorough experimental testing. Like, people have tried over and over and over again to make it not happen, because wouldn't it be amazing if you could drop something and it floated? But lots and lots of testing goes into a scientific law. And the key here that I do want you to remember or write down is that scientific laws, they summarize what happens and predict future observations. So they're talking very specifically about what actually happens, like what is the action that takes place. So for Lavoisier, he developed this law of conservation of mass. So in any chemical reaction, matter is neither created nor destroyed. That one's actually going to come up a lot in this class. Also, feel free to let me know if I'm going too fast. So one or more well-established hypotheses may lead to a scientific theory. So scientific theory, or a model, is different from a scientific law because it's not just saying what happens, it's saying why that happens. Gravity is a hard one to explain. I actually don't know if they have like an actual theory for gravity yet. There's the Higgs boson, but gravity is kind of tricky. So the scientific theory provides an explanation for observations and laws. The short summary is theory equals why, and law equals what, right? So a theory is about why things happen. A law is just what happens. And the cool thing about a theory, I can't remember, Einstein actually had a lot of theories about physics and relativity. His theories predicted behavior well beyond observations that we were able to make, that he was able to make at that time. So there's stuff now with the James Webb Space Telescope that we're able to observe and verify. It's like, oh, Einstein's theory was right way back then, and he had no way to test it. Which is pretty cool and also a little bit scary. Or cool, depending on how you think about it. That the world is built, the universe is built on such strong math, or that we can use mathematical principles to so accurately describe the world and predict out to, things that we can't even test yet. So it was Lavoisier's law of conservation of mass, that led to John Dalton's atomic theory, where he proposed that all matter is made of small, indestructible particles called atoms. And we'll get more into that later. So here's another breakdown of law and theory, right? Laws are what happens, arise from observations, usually observations about a specific phenomenon like gravity, and they may prove to be false. The theory tries to explain why things happen. So I guess to take this back to our example here, the law of Taco Bell may say that every time I eat at Taco Bell, I get sick. Maybe the theory would be food poisoning or, low quality mystery meat. Which, to be fair, I want to clarify, I do like Taco Bell. And I eat there a lot. But inside of this example, And so theories are really they're just taking a different perspective on things, right? We're looking at like, why do things fall when we drop them, or why does wood burn when I hold a match to it? The law just says, those things are going to happen. If you drop something, it falls. If you light wood on fire, it burns. Okay, so which of these statements most represents a scientific theory? So remember, scientific theory is why something happens. Scientific law is what happens. It's hard, right? So let's look at A. Okay, so when the pressure on a sample of an oxygen gas is increased, so if we increase the pressure, the volume of the gas decreases by 10%. Exactly, yeah, that's a what happened, right? We do something, and then it causes some change. For B, the volume of the gas is inversely proportional to its pressure. It's kind of a rephrasing of A. Actually, if we increase the pressure, inversely proportional means increasing one thing will decrease another thing. So increasing pressure decreases volume. For C, a gas is composed of small particles in constant motion. Does that one describe what happens? I guess in a sense you could say it does. I would say that, so the gas is composed, so it's really just telling us like gases are made of small particles. It's not telling us what happens. We're not doing anything to those particles in this sense, and we're not observing anything happening. So that is the scientific theory here. And this last one is that a mass of 15.8 grams and a volume of 10.5 liters.
The other ones already had experimented, that's why they had an answer. And the
Yeah.
B hasn't, it's just telling you, but now we have to.
Yeah. That's a good way to put it. Each of these you can kind of phrase as an answer, or a question and an answer. It's like the question for A would be like, what happens when the pressure on a sample of gas is increased by 10%? The answer being the volume of the gas decreases. I guess it's a little bit harder to put B in terms of a question and an answer, but it is kind of saying that volume of gas is inversely proportional to its pressure. So it says, if you change volume, how does that affect pressure? And the last one is kind of just, I don't know if I would call that a scientific theory or a law. It's just telling us information about a sample. So this image is pretty cool. They wrote the kanji, which is Japanese characters, and they wrote atom in Japanese with atoms. So these are individual iron atoms on top of a copper surface. And this is not exactly what they look like, right? Atoms are really more spherical, but because of the way these are imaged, I think this is a scanning electron microscope, or it might be a scanning tunneling microscope. I don't think we're going to make it to 2, but we'll see. So early scientists such as Lavoisier and Dalton saw patterns in a series of related measurements, and a lot of chemistry involves seeing patterns in things. So if you can find patterns and then replicate those patterns, that will help you out a lot, right? So Lavoisier did his experiments. He said, every time I burned this thing inside of the sealed container, the mass never changed. So he recognized that as a pattern. And that might be indicative or might show something else about the materials that he was burning, and materials in general. And Dalton used Lavoisier's observations and built upon that, right? He came up with why is it when you burn these things that the mass doesn't change? Because if you burn wood, in open air, it becomes ash, and it's a lot lighter than it was before. So really, in that situation, it's turning into smoke. It's turning into CO2 and water. So learning to analyze and interpret data is a very important scientific skill. Learning to see those patterns. So let's pretend we're an early chemists trying to understand the composition of water. Right, so what makes up water? We do some experiment. We know that it's made of hydrogen and oxygen. And we can decompose it so that we can get the exact amount of hydrogen and the exact amount of oxygen for any amount of water that we decompose. Really, we're breaking it apart. So do you notice any patterns in this data? Any patterns at all? Even if it seems too obvious to point out. Yeah, more oxygen every time than there is hydrogen. Even, this is when I was kind of thinking off the bat, is that if we decompose more water, then we get more hydrogen and oxygen. The one that's less visible here, I think it's on the next slide actually. So one of the tricks in sort of trying to identify patterns is sometimes you can just take numbers and divide them. So here if we take, I guess I'll go to the next slide because it does it for me. So if we look at the mass of hydrogen formed and the mass of oxygen formed, and we take that mass of oxygen and divide it by the mass of hydrogen, that gives us a number 8.1. And then if we do it for this larger sample B, right, now it's 5.6 grams of hydrogen, 44.4 grams of oxygen. But if we take oxygen divided by hydrogen, it's 7.9, which is almost the same as 8.1. And then if we use even more, then we get 8.01. So that number staying the same would be a pattern that we could identify. And it means that there's always 8 times the mass of oxygen as there is hydrogen. All right, so we could take this 2.2, multiply that by 8, and we'll get 17.8. So a lot of things that maybe aren't obvious, because like looking at this too, like if I saw these numbers without doing any kind of math or anything, I'd say it's like, well, they're increasing together, but it's hard to see that pattern that when you divide these, they become 8. But you could also do something like taking the mass of the water sample and divide it by the mass of the hydrogen formed, and for each time that you do that, it should be the same. So we do 20 divided by 2.2, that gives me 9.1. 50 divided by 5.6 is 8.93. So every sample of water has the same mass of, or has a proportional mass of hydrogen in it. And this is one of those things, so seeing pattern in data requires creativity, and it's also a learned skill, right? The more data that you look at and try to analyze, the more that you're going to see those patterns, because you'll learn different patterns to look for. Another important skill is learning how to interpret graphs, because oftentimes research and data are shown and given as graphs because they summarize a lot of data very nicely, and it makes it easy to see trends. So for example, here we've got x-axis, which is this bottom one, and a y-axis, which is the vertical one. You got to make sure you know what each axis represents, right? So we got the years from like a little before 1860 all the way up to 2020, and then over here it's the carbon dioxide concentration in the atmosphere, and that's in units of parts per million. So this, like 300 parts per million, means there'd be 300 molecules of carbon dioxide in a million molecules of other air particles. So this is showing, right, looking at this, we can see that we're starting low here, and as time goes on, that concentration of carbon dioxide increases. And we could even say from this that over time, it started to increase faster as this slope gets steeper. The other thing that you can do with a graph like this is you can pull numbers off of it. So let's say we wanted to know in the year 1940 how much carbon dioxide was in the air in 1940. So I'm going to zoom this. So then we look at 1940, right, and we draw a line up to where that intersects with the data, and then we could draw that line basically over to the side here. See that this is 300. This is one of the things reading a graph. You got to figure out what each of the tick marks mean. This will actually be important in lab too, because some of the beakers or the graduated cylinders are weird. So this is 300 and that's 320. So what's this point in between? 310, right? It's just halfway in between. So we're a little above 310. And we'll talk about estimation too, I guess on Wednesday, because we're getting to the end here. But when you're estimating data, we know that this is 310, and we're a little bit above that. So the best we can really do here is like 312, maybe. So we can say there's 312, that's 21, parts per million carbon dioxide, CO2, in 1940. So we can't estimate any finer than that, right? We couldn't say that that's 312.5 because we don't have any units even for the ones place. That's our guess. We'll talk more about that in chapter 2. So how to succeed in chemistry? I think it comes down to starting to look at the world around you and ask, like, why is this plastic clear? Like, why does this laser work the way it does? And why, when I turn off or when I like open up the focus, like it makes this huge dot. And then why, like that doesn't look like a regular flashlight beam either, right? It's like spotted. So asking those questions about the world around you, this class is designed to give you the tools to try and answer those questions. That does mean there's a lot of tools. There's 17 chapters that we have to get through. This one is huge. This one is so huge, and I mention it all the time. Just be willing to do calculations and be willing to start problems without knowing if you're starting it correctly sometimes. But then look at that. It's like start the problem. If you get stuck, then maybe you started it the wrong way. But a lot of times, I will say 90% of the time when students have questions with a problem, it's because they're staring at a blank sheet of paper and trying to do it in their head first. And there are so many little things that you have to keep track of that if you try to do it all in your head, you're never going to write anything down. So as soon as you start writing out problems, sometimes the answer becomes evident because you've got this on the page now and you can see what you're working with rather than trying to work through it in your head. So don't be afraid to use a lot of paper. Like go to Staples, I think a ream of paper is like $4 and that's 500 sheets of printer paper, right? Or, because you don't have to get a notebook, just use printer paper. Like get a pile of scratch paper. I bet even if you went to the library, they have scratch paper. Or there's copy and mail, they might have it too. Stuff that people printed single-sided. You gotta be committed to learning the material. This class does require a lot of outside study time. You should be going to my office hours or to the Mesa Center or to the math lab or talking with a tutor, form study groups. All of that stuff is going to be super, super, super helpful. And it'll sort of help you keep you accountable, staying on top of the work because you don't want to fall behind because it just piles up. It doesn't get better. Yeah, do your homework. Oh, actually, I think I forgot to mention about homework. The homework is show work and you get points. So I'm not going to go through and grade every single individual question. They're odd numbers anyway, so the answers are on the back of the book. But I do require that you show work. And I will be going through and looking at all of them. Yeah, okay. So this last quote from this Nobel Prize winner. I like the idea that human beings can do anything they want to. They need to be trained sometimes, and they need a teacher to awaken the intelligence within them. But to be a chemist requires no special talent, I'm glad to say. Anyone can do it with hard work and dedication. This stuff, I believe, is truly within your grasp. You can do it, you can learn it. It's going to require that you stare at problems sometimes, that you write things out a bunch of times, so that your hand hurts and you have a headache. But if you have a headache, unless you had recently had if you had recently had a concussion and you have a headache, then stop. But barring that, I was in that situation once. But barring that, you should feel mentally fatigued when you're done studying. If you don't, then you didn't study. And if you're just reading through your own notes, it's easy to like watch me do a problem or see somebody do a problem on YouTube or look at a problem already worked out and say, oh, that makes sense. The hard part is trying to replicate it. So make sure you're doing that. Yeah, it's all the odd problems, and they're in the back of the book. All right, well, that's 942. So we'll get to chapter 2 on Wednesday then.